Hello everyone, welcome back to the Game Engine Development Workshop series. I'll just go over a quick recap of what we finished off last time, which was this very cool sort of dynamic map loading system where we just have a text file here. We can set some settings like the background color, the scale, and then sort of create these structures called chunks, which right now we just render all at the same time, but eventually that'll be used to sort of more efficiently split up our world. So you can see here I have a pattern that just consists of two tiles here horizontally right next to each other, and then I use that pattern twice. When I run, I get one pattern here and one pattern up here. It's very easy to come in here, just copy this line, change that to 150, and I should get a third pattern right in the middle there, just like that. So very simple. Pretty easy to use and perfectly good for our purposes. So today, we're sort of going to be adding like more or less a layer of polish onto this map system. Now, this normally is, I don't think I would go in this order. What we're doing today is lighting. So we're going to add like a new type, I suppose, to our map here, where we can say like light and then give the chords and a color, and it'll put some lighting effects, just apply those to our whole world. And like I was saying, normally I wouldn't go in this order. I think lighting is something you would do after you have some other systems in place. So just I've probably talked about this several times, but the sort of remaining roadmap that we have left, we just finished off map data. We'll come back here and there and add some more stuff to it, but for the most part, the system is done. And what we're doing now, or from now on, is lighting, which we're starting today. Then we're going to do dynamics, which is just, I don't know if that's actually what it's called, but that's my word for stuff that actually moves around the screen. Because right now, even though we can move stuff around on our screen, that data isn't actually moving. It's the camera is moving, and the data is being transformed relative to the camera. But obviously, if you want to have like a playable game, pretty much, you're going to need some character that actually is able to move around in the world. That's pretty important. So that's what we're going to do after this. And then after dynamics, we're going to do hitboxes, because you don't want your player to just be able to pass through walls and everything. So those normally, I think you would probably do before lighting, just because they're more important. Like lighting is more of a polish thing, but those are like necessary core systems. But it turns out those are two pretty hefty systems. Like they are uh, not only complicated, like theoretically, and able to do everything efficiently. Um, Dynamics are more so complicated, just getting everything to render efficiently. So sort of integrating that with your graphics library. And hitboxes are a whole nother thing. Like we're only using rectangles here, so the actual math for detecting and resolving collisions is pretty simple. But being able to scale that up efficiently, to like the size of a whole world, is a lot trickier. And so those systems I've decided to do after lighting, just because lighting, I think we'll probably be able to get through all of it today. And then those dynamics and hitboxes will probably take 2 or 3 episodes each. And then, of course, at the end, we're doing scripting. So that's why I decided to do lighting first, even though it is a bit weird, bit of a strange decision. But anyways, let's get into it. So the first thing I'm going to say about our lighting system, just so that you have this in your mind as you're watching the rest of this, is that our lighting system will be inefficient. It will be slow. You should not implement a lighting system as I'm about to. Now, it wouldn't be too difficult to change this if you wanted to yourself and sort of make it more efficient. But the reason I've gone with a simpler one is because like it's only inefficient when you have a lot of lights. And lighting, like it was not a very highly requested feature in the surveys. Like, again, I sort of wanted to shave off time wherever I could just so that we could get to the scripting language at the end, because that's what the most people wanted to do. It's also what I want to do. I think that's the most interesting part. So our lighting system will be slightly inefficient, but as we'll see as I start describing, our sort of map philosophy here of like we have a map, but it's comprised of various self-contained chunks that will help sort of mitigate the inefficiencies if you want to have a world with tons and tons of lights. But before we get into any of that at all, we need to just talk about like lighting itself, because it is a pretty complicated topic. I'm obviously right, like 3D rendering is not even perfected even now. But we're just doing 2D stuff, and it's still sort of like a bit of math to get your head around. So yes, I think I'll probably talk more about how you could like optimize this, and why my system here is particularly inefficient, as we get into it. But let's just start out with some math. I think we can jump right into our shader here and get going. So we'll have, for now, we'll just take in a single uniform, and that will be our light. We'll just have one light. It'll just be a vec3. I'll call that U light. Okay, now here I'm going to write 4 lines of code that is a bit of linear algebra, and I will explain it. I'll draw a nice diagram in a second. We also need to do that. Yeah. You can see a dot product here, and lots of normalization going on. Okay, so essentially this just takes our light and calculates the effect of that light on the current pixel, and we store it in this vec4 light, and then we'll just multiply that by our texture. And for now, this is just white light. It's all grayscale, because we just have a position vector here, but eventually we'll have a color vector as well, so you can add some nice color to your lights. Now, I did forget, we also need to take in another vec2 here, actually, v underscore position. And this will just come directly from our vertex shader. And of course, I will explain this as well. Okay, so before I actually run this, I think I'll just go ahead and explain. I'll draw a nice diagram that hopefully will help you sort of visualize what's going on here. But actually, the first thing I'll explain is that position vector, what's going on there. Oh, I have, this is I guess a bit of a sneak peek of some of the diagrams I'll be using for our hitbox system. Using quad trees. Okay, so I already have talked about this a little bit near the beginning of this when we just started doing OpenGL stuff, but I'd figured I'd do it again just because now that you have a bit more experience with OpenGL, it'll probably make more sense, and also it's just good to refresh your memory on it. So I have a triangle here with 3 vertices, obviously it's a triangle, and I want to like calculate some value for an arbitrary pixel within this triangle. And the way OpenGL does this is it will actually interpolate between the values for you. So like, say my position at C here is like -1 in the x and 0 in the y, and my position at B is 1 in the x and 0 in the y, and A is 1 in the x and 1 in the y. This sort of is analogous to our v position variable here that we're passing from our vertex to our fragment shader. So this I position that we take in here would be these, values, like the actual values at the vertices. But then This yellow dot here will be some mix of these. It'll be OpenGL will interpolate across these three ranges for us, or I guess two ranges, and depending on the position of this pixel relative to each of the vertices, it will weight the value of those vertices differently. So once again, these three actual vertices here, A, B, and C, are part of our vertex data. They are what our what our vertex shader operates on. This layout location equals 0, reading it from our vertex buffer. But then we output it to this other vec2 here. We just copied in there, and the fragment shader taking it in will interpolate across those three values for every pixel. So this v position is essentially just the position in world coordinates of our of the pixel that we are currently shading. And that's important here because we have in our vertex shader, like the main function of it is to transform our vertex data from world coordinates, this sort of like fake made up coordinate space that we've designed, that in our case is in terms of like simulated pixels. So it takes that data and transforms it into the OpenGL range of -1 to 1. But we're not passing anything about this. We don't care about its screen space position. We're just passing it straight up the world space position. And the reason for this is that we're using it for calculations with our light position vector here, and we want our light position is obviously also going to be in world space. So it's very important that we make sure those are in the same like abstract mathematical spaces there. So that's just v position, pretty simple. I'll go ahead and delete this, and now I'll draw a nice diagram of like what's actually going on. Just give you some axes here for reference. So we have positive x to the right, of course, but now this is going to be positive z. So this is sort of like a side view of what's happening in our game. And obviously this will be taking place in actually 3 dimensions, but I've omitted y because I don't know how to draw that, and also it's not necessary to get the concept. So I have these extremely perfectly straight lines here representing our vectors. I'll just get some names to these. So the red one is normal. This blue one is lighter. And then this blue point up here is U light, our actual light's position in 3D space. And then this red point down here is V position, so our current pixel's position in world space. And then this sort of horizontal line here is our surface, or our texture. Because remember, everything we're doing is in 2D, essentially, until this point where we're sort of introducing like a quasi third dimension just for lighting. But you can see here in our GL position assignment, we just set the z coordinate to a flat 0 every time, flat 0. So that's why I've sort of drawn this way, just so I think it helps you visualize that like the texture is just a flat thing on the XY plane. It has no magnitude in z, and you can see here that the light will have some magnitude in z, and so it can interact with this in interesting ways. So let's go through each of these components that I've labeled here and see like what they are in our shaders. So let's start with U light, obviously. I sort of already said, but that is the world space position of our light. And what we need to do in order to calculate the effect of that light on any given pixel is we need to do some basic vector math. It's really just, it ends up being just a single dot product here. And the reason that it's the dot product is, I'm not going to draw this. I'll assume you know what a dot product is, but like, or sort of how it works. But if our light is directly above the pixel we're shading, then we want the maximum intensity of that light. So the dot product of that would resolve to 1 in this case, because our two vectors here that we're taking the dot product of, normal is a normalized vector, and lighter is also a normalized vector. So this dot product will range from 0 to 1, or -1 to 1, but we're clamping it to 0 here because we don't want any weird effects. So yeah, if our light source is directly above the current pixel, then our dot product will be 1. And if it's someplace off far in the distance, say infinity, then this dot product will asymptotically approach 0. But, you know, that's sort of the edge case. What we're really more worried about is like the immediate area around where this light hits and how that will be shaded. So that's what U light is. It's just the coordinates of our light, our current light source. Now, light direction is the vector between our light position and our current pixel position. And you know, if you have two vectors and you subtract them, you essentially just get a line drawn between those two vectors. As shown here, this blue line is light dir, so the line between our light position and our pixel position. Now, this diagram is slightly misleading because if you see here in our shader, we're actually normalizing that because we don't care about the magnitude. We don't care about like the distance between our light and the pixel. We only care about the angle of that vector relative to our surface. So that's why we normalize it here, but I just I didn't do that here because it'd be too hard. Okay, so that's light dir, and the normal here. This probably seems like the weirdest one just because I've hard coded it. This is 0, 0, 1, so 0 magnitude in x and y and 1 magnitude in z. And the reason I can hard code this is because we are setting our z coordinate to 0 for every case. For all of our textures, they have no z magnitude. And really, this would be like traditionally achieved with the cross product of two vectors. The sort of normal vector to the surface, to a surface, is the vector perpendicular to that. And so in this case, because our textures only have magnitude in the x and y axes, but none in the z, the normal to that is 0 in x and y, and 1 in the z. So this sort of normal red vector will always stick straight up, straight out from our textures. And what that means, I guess I can draw another little thing up here, is our camera is sort of up here, you know, like viewing this texture from above. And so the normal is like pointing at our camera, and obviously that's what we want because we need to calculate the effects of this light as viewed from the camera, from the observer, from the player. And so that's why we use normal pointing straight up towards the camera. Now I've drawn this theta here, which is just sort of the stand-in for the angle between our light direction vector and our surface normal. But if you look in our shader, we don't actually do anything with theta. And this is pretty cool because vector math kind of allows us to sidestep expensive, slow trigonometry equations while still sort of indirectly accounting for them. Because the dot product, the formula for that, you remember, is so A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between them. So you can see here there is this like cosine term. It's definitely part of this result, but we have this additional shorthand, which is like for 2D vectors, it's just A dot x times B dot x plus A dot y times B dot y. And so we can get the same value without doing any trig, but still accounting for it, which is very cool. And you know, GPUs are very, very fast at vector stuff, but classically computers are slow at trigonometry. So that's sort of like why we use the dot product, I guess, there, because we are interested in the relationship between the light and the current pixel. Only the angle. That's all we care about because that determines how much of that light will bounce off the surface and towards the camera. And that's why we do normalize everything as well, because we don't care about magnitude, only angle. And so this dot product, taking in these two normalized vectors, will just account for that. So that gives us a value between 0 and 1, which we then essentially just turn into a vec4 here, a vec3 with that single value between 0 and 1 as all three components, so x, y, and z. and then we're multiplying that by a texture, so that becomes RGB. So we have the same intensity in red, green, and blue, which is white light. But as I was saying, eventually we'll just take this intensity and multiply by a color vector as well, and then multiply that whole thing by the texture, so we can sort of tint everything. So hopefully that made sense. This is pretty simple. I'm not claiming to have like a full understanding of it, but like I know enough, I guess, to like I don't know why it works, but I know how it works. I guess that's a good way to explain it. And really, with all this vector math stuff, that's kind of where most people end up. And this frustrates me endlessly because I'm someone who like I really like to understand everything in the most general sense so that I can apply it however I need. But this sort of 3D vector math, this is sort of 3D stuff, but especially like the more tricky actual 3D like projection matrices and all of that when you're doing 3D graphics is notoriously mysterious and very difficult. And one of the guys who sort of like spearheaded, I guess, the 3D game revolution in the early 90s was John Carmack at id Software, and he said in an interview years later that like people would always come to him like thinking he was some massive like linear algebra guru and he understood everything, and he said, no, I don't know, I just I copied it out of a textbook, I don't know how it works. So you know, even the giants in our industry don't really understand this. It was just sort of dreamed up in a lab, and I don't know, probably the 60s to the 80s, there was tons of research going on with this. And we can just use it today and not really understand how it works exactly, which is nice. Okay, so now we'll go ahead and we'll just add that color vector here. So I'll separate this out into light position instead of just light, so it's a bit more clear. And then all we're going to do is replace this with intensity times U light color. Like that. Okay. So at this point, we can actually test this in our main file here. So let's get our shader. Do I have a Git shader? I don't. And we'll probably also have to add, we'll have to add set uniform 3f because we're now using 3D or 3-component vectors. Need x, y, and z. Might also have to write this in our shader. Yes, we do. So still a bit of a hassle just having to come and define all this manually, but ultimately very simple because we have this nice set uniform thing that templatized everything for us. Okay, so I think, for now I'll just add like a hacky like get shaders method, but eventually we won't need that. So that we can set it from our main file. Oh, this is yelling at me. I might move this up into up above here just so I can write that right there. Yeah, there we go. So the order that you define things in classes does matter. That seems weird to me. Like it seems like it shouldn't. I'm sure there's a good reason behind it, but either way, I just had to move this up here so that it knows what this shaders type is. Okay, so we can now do render.getShaders.setUniform 3f, and we called them light pause and light color. So for now, I'll just set this at 0, 0, and 1. So that should be the center of our coordinate system and 1 unit in the z-axis, which means towards the camera, like out of the screen towards the player. And this may depend on the graphics API you're using, but in OpenGL, the camera, like by default, it looks down it looks towards negative z, I guess. So some point like infinitely far away in the center of your screen is negative infinity in the z-axis, which means that positive infinity is out of the screen towards the player. And then light color for now, I'll just set that to 111, so we just get some white light there. And let's run this and see what we get. Hopefully something good. There we go. So it's very, very dim, but you can see here that sort of outside of the reach of my light, all of our pixels are just colored black, and this like extra group up here is totally black. And we'll look at near the end of today, I'll sort of give you guys some more interesting lighting equations that I think look much nicer in this sort of artificially pixelated style of game. But this is just sort of the classic, like very clean, single dot product, mathematically pure way to do it. So we'll stick with that for now. But if I want to like increase the intensity of this light, all I have to do is pull the light further away from the camera. Because in our shader here, we're not actually like scaling the intensity based on the distance of the light. If we were going to do that, we would just, I'm not sure exactly how, so don't quote me on this, but the general gist of this would be we would have our intensity value here, and then we would divide it, or do some sort of somewhat inverse operation with the non-normalized distance vector between our position and our light. So actually get like the number of pixels in quotes between our light and the current pixel we're shading, and then use that to scale. But for now, our light is just like sort of infinitely bright, I suppose, and the only determining factor of how bright it appears at any given pixel is the angle between those. So obviously, if I move this further away from the texture, further towards the user, then there's a much wider range of space that has an angle that gives a brighter value. So you could probably, you can see it even all the way over here. And you can see here that the like near the center of it, it's much more spread out, where before it was a very concentrated point. So that's just like the basics of what's going on here. So this is all good. This is basically all we need, except as is often the case, we now have the problem of scalability. We have one light here. We want infinite lights. I don't know, like our user should be able to set however many lights they want. And so we need to come up with some system in our shaders to handle like arrays of lights, I guess. But also then a system to sort of hook it into our map loading pipeline so that the user can define lights in their map files and they'll show up there. The first thing we'll do is just create a very simple single header file called light.h, somewhat similar to tile.h, just sort of a structure for, I'll go ahead and include PCH, just for passing around light data. So we'll have a vec2 of position, because really, like even though this is a vec3, the way I prefer to think about it, because everything else we're doing is in 2 dimensions, coordinate-wise, I prefer to think of this vec3 as like having 2 components. The x and y component are the actual coordinates of it, like left, right, up, and down on the screen, right? But then the z component, which, as I've explained, technically is actually a z-axis like magnitude that we are using. We are relying on that in our calculation here. As you saw here, how I just manipulated this value, it's easier for me to think about that as intensity, where the higher the z value, the brighter or the more effect that light will have on the scene. And so I'll just sort of artificially split that up here into a vec2 and then a single float called intensity. And then our color vector is just going to be an array of 3 floats. And then I'll go ahead and define sort of a maximum limit. I'll just set it to 128, but really this could be whatever you want, 1024 maybe, doesn't matter, this stuff is small. And the reason we need this is because You can't have arbitrarily sized arrays. Well, that's not true. You can, but the way we're doing it, you can't. Like those arbitrarily sized arrays have to be stored in this other structure called a SSBO, shader storage buffer object, which is just inherently slower than uniforms and what we're going to be doing just in a minute here called a uniform buffer, because it's uniform buffer is sort of stored in the local like shared cache of a shader on the GPU, but SSBOs are stored in a shader's like global memory, basically, like somewhere in the 6 gigs or whatever of VRAM that you have. And so even though it's technically just like dereferencing a pointer, I've done some benchmarking with that, and compared to uniform buffers, I guess a way you could think about this that's sort of analogous to C++ is a uniform buffer is like a stack allocated array. You know, like if I did int R5 like that, it's stored on the stack, it's right there. But then an SSB or a shader storage buffer object is going to be allocated on the heap like that. And there's a pretty massive difference actually between having something in global GPU memory and something versus something in a shared sort of cache. I've done some benchmarking and it was about double the performance using uniform buffers compared to shader storage buffers. So we're definitely going to be using uniform buffers for this just because it's so simple, but shader storage buffers do have their uses. We're not going to get into that though. That's just some interesting background knowledge if you guys want. But yeah, anyways, we need to define this sort of maximum light count here because we do need to provide our arrays in GLSL with a hard-coded integer constant, like a compile time constant value, the length of it, provided it's not in an SSBO. Okay, so we'll get into this later. For now, let's just sort of write the infrastructure in our C++. So yeah, we could do something similar to what we have for our textures and our texture frames here, which is just have just a uniform like array of these of vec3s basically that are our lights. There are two sort of main reasons not to do this. One is that there is actually a hard limit on how many uniforms you can take in per shader stage. This is something you can query, very similar to like GL get max texture unit count or whatever it is that we get the number of texture slots we have. You can get like I don't remember what it's called, but like max number of uniform variables per shader stage, and you're in danger of hitting that. But also, it's using a uniform buffer is potentially a lot faster updating wise than using these regular uniforms, because what a uniform buffer does is it's basically a single block of memory, kind of like a texture actually. It's bound in a very similar way to how textures are bound. But what it allows us to do is sort of swap out groups of uniforms all at once. So say we had an array of 10,000 vec3s here, each that's a different light. And we want to, for whatever reason, change all of those lights or change a significant number of those lights all at once in a single frame. Then we'd have to go through and set each of those uniforms in that array individually. But with a uniform buffer, we can sort of have those differences in light pre-calculated almost. So like an example I can think of when you would do something like this is, say you have in your map you have like a sort of flickering torch or like a campfire that flickers, and so you want the light intensity to change with time in sort of a pattern. Then you could have a separate uniform buffer for each of those different like states of flickering, and rather than going through and changing all of the different light position, like the intensities for all of those campfires in your scene, you just have those pre-calculated in separate uniform buffers, and you can like swap out the uniform buffers all at once. So you just move chunks of data, sort of like you can think of it as effectively moving chunks of data and swapping them out. But really all it is binding a different thing to the same spot, just like our textures. It's just sort of changing where that slot points. So that's like the main reason you would use a uniform buffer. But we're not going to be doing this. Like that example I gave, I think is something that is a valid use for one. But I'm not going to go that far. You could. But really, the main reason we're doing this, aside from just making our code clean and like easy to read, is that I think it's probably valuable for you to see because it's a very common thing and it's not that hard to set up. Okay, so we are actually going to be coming back to our graphics library here. Just creating a new class called uniform buffer. And before I forget, I'll go ahead and include that in our all.h here. Just sometime after buffer and sometime before render, I think, is where we'll be using it. So this is a buffer, a GL buffer, and the target is GL uniform buffer. Just like how our index buffer is GL element array buffer and our vertex buffer is GL array buffer, this is uniform buffer. So we are, because a buffer is a GL object, it sort of has this inherent like ID field, but we are going to store more or less another ID field in our uniform buffer called the slot. And this is analogous to the texture slot, like that I'll just show you, that we provide to our textures bind function. It's very similar to this. Obviously you use different methods, but it's like the same concept of you bind this thing to like one of an array of different pointers that are available for it. And you could absolutely do the same thing we have with texture, where you supply that to the bind function. But in our case, we're like I said, I'm not going to be using these to swap between different buffers, so I've just sort of stored it as part of the object state. It's not going to be something that needs to change from frame to frame. Okay, so our very simple constructor there. Of course, I'm going to delete all of the rest of this because I'm always paranoid about that. We'll just sort of provide another thing here. Deleting UB so that we know when it's gone. Okay, so our bind function is going to be a bit different. We are going to need to override the default buffer bind. I'll go ahead and have a getter for our slot index there. Now let's look at the buffer. Where is it? Buffer bind. Yeah, there we go. So GL bind buffer to target and MID. So we still need to do this, obviously. Like you have to tell, you have to send this to the GL uniform buffer spot. Now we could just like copy this and sort of hard code GL uniform buffer as our target, and that wouldn't be too terrible because it is just one line of code. But sort of an interesting syntax you can do, and I forgot to. I always like to put the specialization there on the parent. Is you can call the parent class's implementation like this. So this is something I sort of talked about a while ago when I gave a description of virtual functions, where like when you override a parent class's function, that function will not be called by default, as it will be for constructors and destructors, but you can still access it. It's much like Java, where you could do super.bind, I think would be the analogy here. So we do need to do that, but once we've bound it, we need to do this additional call called GL bind buffer range. And the target is GL uniform buffer. The index we give it is im slot. The buffer is just the ID of our buffer. The offset is 0, and the size is going to be im count times size of float. So this just means like bind this essentially to the texture slot, or the uniform buffer object slot that we've given to this object. and give access to the whole range. So buffer range, it lets you specify like part of this buffer that you would like the GPU to be able to access, but because we just give it 0 to the number of floats we have, we're giving it access to the whole thing. I'm not sure where exactly you'd want to use this, or what the reason would be. Like, I could see maybe how it could give some performance advantage if it has to only copy then a certain sort of sub range of the whole buffer. But I'm not sure. We're just going to do the whole thing. Okay, so that's all we need in our graphics library. Our handy buffer base class makes that very easy. Now we're going to come back to our chunk and add another vector to our chunk constructor, a vector of lights. And include that here, just like that. And we'll need now to actually store these lights in our chunk. So each chunk will have its own sort of group of lights. And this is what I was talking about at the beginning of eventually the like inefficiencies incurred by our totally dynamic lighting system will be sort of mitigated. They will be localized to each chunk because each chunk takes care of its own lights. But again, for right now, we're just drawing all of our chunks at once, which is not great, but eventually we will change that so we're only drawing the chunk that the player is in. So that'll drastically improve performance if you have a ton of lights everywhere. Okay. And then in our chunk here, our constructor, go ahead and set these. That should be lights, not light. Set it to null pointer by default. And light count to 0. And then all the way down here, actually assigned to it. We'll have auto pointer equals constructor.lights.data. So remember, lights here is a standard vector, and .data just gives you like a pointer to the first element of that array. And the reason I have to store this separately, I'll show you in a bit. So we want our light count, like the number of lights that we're storing in this buffer, to be the minimum of like the maximum number of lights that we support, which is defined here just as some constant. So the minimum of that and the actual number of lights that we've been given. So if in some case the user has more lights in their map than our system can support, it won't crash and just break. It'll just chop it off. It'll just truncate whatever list they've given us. And now we actually need to create our uniform buffer. The count will be mlight count. Is that right, actually? That doesn't seem right. No, I guess it is. Light count times the size of a light in bytes divided by the size of a float. And then the data we're giving it will be this pointer as a float pointer. Because remember, our vector stores lights here. And so this pointer gives us a pointer to the first element of that, which is a light pointer. But our uniform buffer, all of our buffers just store floats. Well, I guess our index buffer stores uints, but our uniform buffer stores floats. And it just so happens that our light vector also just stores floats. You have a float intensity, 3 floats here, and then math vec2, of course, just has 2 floats. So this is essentially 6 floats laid out contiguously in memory. So we can actually pass this as a float pointer, and it will be sort of valid. But in order to do that, we have to pun it. And that's why I stored this pointer as like a local variable, because you can't pun this, because that's like a R value. And then our slot will just give 0. Okay. So this we will be coming back to. Like this syntax here should be a bit confusing, and it should seem suspicious. It kind of is, but mostly it works the way I just described. Oh, and then of course our move constructor here, we need to move our light buffer. And then set other dot lights equal to null pointer, just so that when that gets destroyed by our destructor, which I also forgot to write, dang. So when other gets destroyed by its destructor, this mlights pointer is just null pointer, so this will be a no op instead of actually deleting the buffer, and then our new buffer has a pointer to that deleted memory, and it's an error. So that's just sort of the basic move constructor syntax there. Okay, so now we will actually integrate this into our map system so we can create some lights in our files. So we'll add another chunk function here called add light. And then within our chunk functions array down here, create a new keyword called light and map that to add light. Okay. So this will be a very simple function. Let's copy this header, I guess. Oh, and I probably need to also include light.h. So we'll just create a default initialized light there, and then replace all its values with what we read in. So order here is x, then y, then intensity, then color, and then of course our light is contained within our chunk, so we need to apply the chunks, like sort of base coordinates, to our light. And then we will just push that back into our array. Okay. And then obviously this chunk constructor, this lights, will be received in our actual constructor here and turned into this uniform buffer. Now we're mostly done, but we do have to like set our shader up so that we can actually bind uniform buffer objects, because they are somewhat different. Like I said, there's sort of a mix between like textures and uniforms, how you bind them. So there are actually different functions that we'll have to write in our shader here. Now, unfortunately, the way you get like the index or the ID of a uniform buffer within your shader is a different function from this get uniform location. It's get uniform block index. Very good, consistent naming there. Makes it super clear what's going on. But the rest of this functionality will be the same. So we'll actually sort of templatize this just a bit further. And just take in another function here. And then just call that function. So now we'll need int get uniform location for the one we just had, and we'll call get location on GL get uniform location. Then we'll also have get uniform block location, which will be GL get uniform block index. There it is. Okay, and now up here we will have a set uniform block. Now we don't have a wrapper, like the way that you set uniforms is also different, so we can't use this set uniform function, but we're not going to have to reuse this, and it's not a lot of code anyways. So we'll just get the index of the uniform block with the given name. If it doesn't exist, we'll return. Probably throw an error. Oh, actually no. Our get location function will throw an error here. It'll say uniform not found, so we just have to return here. Don't need to print anything. Then we'll bind ourselves, bind the given buffer, and then to call GL uniform block binding on this program, the location within our program, and the slot that we want to bind our buffer to. And that'll bind this bound UBO to this UBO slot. Okay. Now, let's sort of take this one step up the chain into our engine renderer here, and add a set uniform block function to our shaders struct. I guess we const char name, doesn't matter. And what was the last thing? I forgot. I think it's just a uniform. I think it was a reference. Maybe it was a pointer. We'll find out. And that'll be GFX. Then for now, we'll just call statics.set uniform block. Name buffer, and it is a const reference. Okay. And then in here, we can sort of get rid of this get shaders method, and we'll just have a method called setLights, which will just take in a whole buffer and set all of them all at once. So mshaders.setUniform1i. Oh, we'll also need to define that because we need to give it the number of lights, which I'll talk about in a minute. But we already have this set uniform block called uLights. We'll give it lights. Yeah, so just real quick, I guess we've never used set uniform 1i, which is very strange. I guess we've only used float. But that is a super easy change. Just like that. And then obviously we need to wrap it here. There we go. And then we can sort of take this just one step further and do it automatically in our chunks draw function, so that it'll go ahead and bind its own light buffer for us. So set lights, light count, and its lights buffer. Because I can't really think of a scenario where you'd want to like draw everything without binding your lights, so we'll just go ahead and do it all at once. Okay, so the reason we need to set this uniform 1i here, this u light count, is that even though we will have an array here of some hard-coded length, we're not always going to be taking up all of the spots in that array, right? So we don't want to loop through the whole thing because it'll just contain a bunch of zeros wherever we haven't set stuff, which is useless. That's wasted processing time. So we'll have this sort of additional uniform int just to say how many lights we've actually set, and we'll just loop up to that point instead of through the whole thing. Okay, so I'll go ahead and define our max light count as 10. I'll just do 100 actually. We don't need 1024. We'll just keep it 100 for now, but you could very easily change this if you want. Okay, now you may not have known you could do this in GLSL, but it does have like some things, some nice quality of life things similar to C. You can sort of have these preprocessor macros here, just constants for the whole shader, and you can actually define custom structures, which is what we're going to do here. So instead of storing our lights as just two separate vec3s, we can store them in this sort of grouping of two vec3s, position and color. Okay, now we're actually going to set up our uniform buffer. And this has some new syntax, which we will talk about. We'll not only talk about, but examine in detail in a minute here, once we get everything written. And within this buffer, we will just have an array of lights of length max light count. So the syntax is kind of weird here, like it has two names, it seems. This is just like the name of this type of block, but this is the actual instance name. So this is the one we're going to be using, and that's why you see here I'm binding to, or sorry, no, I described that completely wrong. This is the name that you bind to from outside. Well, I guess this is the name you actually bind to. So you can see here in our renderer, we are binding to the set uniform block of u_lights. But then within our shader here, we will access this array by u_light.light. So this is like the in shader name for it. And I'm not sure exactly why that's how it is, but. And then we'll just have our light count there. And at this point, we can basically just take what we already have and put it in a loop. But we will need some external variable here to store the color, like the overall effect of all of these lights for the given pixel. I want it to be completely additive, which is just like intuitive, what you'd expect. And then here at the end, instead of just setting this light variable, we'll do color plus equals intensity times our light color. And I'll come back to those variables in a minute because they're now messed up. But then at the end, we need to clamp everything back into the range of 0 to 1. Because if we have a bunch of lights here, this could add a bunch of stuff, and this could end up with weird values. So we'll just go ahead and clamp it between 0 and 1, and then multiply our texture by a vec4 of color with 1. Because color is a vec3, but our texture returns a vec4, and oColor expects a vec4, so we need to give it a vec4. The reason this is 1 instead of 0 is because our texture could have some opacity value, which will be stored in the W position of the vec4, the last element, and we don't want to mess that up, so make sure that's 1 instead of 0. Okay, so now we just got to go through and change our names. We can delete these old uniforms here, our light pause and light color. This will be now uLight.light at I.pause. So uLight is our buffer, uLight.light is our array of lights within that buffer, and then light.pause and light.color are the individual components of a single light. So we need the position here, and then down here we need the color. Okay, so now we should, like we've sort of done this end to end already. I'm sure I've messed up a bunch of stuff, but we can go ahead and test it. If we just put in a single light, again, I'll just start out with white. So looking at our map thing here, we can see the order is X, Y, and then intensity. So we want it at the origin 0, 0, and then intensity will just be 1. Or I'll actually make that 10 so that it matches what we have currently. And then color is just these next 3. So 1, 2, 3, RGB, that's going to be white. Oh yes, and then delete this example we had here. First, let's even see if it just compiles. I'm sure I made some mistake. That was a lot of coding. Okay, here we go. So undefined type renderer. It's probably just in my chunk.draw. So I could include renderer here, but I think I'll go ahead and do the proper way and just sort of move this into our C++ file. That, and that should solve that. There we go. Now let's run, and fingers crossed, we'll get something cool. Okay, so we kind of do. It does seem that this is offset a little bit. I guess, yeah, I'm not sure if this will show up on the video because YouTube compresses everything, but like there are sort of faint bands here. But what I was expecting is our the like position, the actual position, the center of our light to be at this corner as it was before, but it seems to be somewhere down here. But it is working mostly, which is a good sign. There was some lighting effects. Now I'm gonna suspect, yeah, this is placing it. Okay, yeah, so our thing is actually offset by 100. Um, so now it should show up in the correct place. And there we go. Sort of. So this is not white light, obviously. This is yellow light, which is confusing because the background is also yellow right now. But I'll just go ahead and change the background just to prove to you that this isn't some weird mixing there. The light itself is actually yellow, even though we very clearly set RGB to the same, to 1, which should be white. So why is this? Well, let's go back to our shader here, to this buffer declaration that I just sort of glossed over, this layout standard 140. I'm going to go through sort of a slight debugging process with you here, even though this is, staged, know what's going on. But just I thought it would be good to show you some of like the like documentation and how I actually solved this problem, because even though I've done this before, obviously all this stuff is like crazy complicated. There's a lot of moving parts, and so you will mess stuff up like constantly. And even when you've done it before, it can be very frustrating. But there is tons of great documentation online, like official documentation, YouTube videos, and Stack Overflow posts, obviously. So this sort of scenario here, where I was expecting it to be white and it turned out yellow, happened while I was designing this, and so I thought it would be cool to just show you like the process I went through of figuring out what was going wrong. So I've pulled up here the page for an interface block. Now this you can see here it says a group of GL input output. So those are our like our in and out things here. You can actually you don't have to just supply primitives like vec and float. You can supply sort of structures, blocks, like this as input and output. So that's what that means. Uniform blocks, which is what we're using, and shader storage, storage buffer, so SSBOs, which is the other thing I talked about that we will not be using. So the issue going on here is with our memory layout. So let's sort of read a bit of this. Because memory layout, like, and it probably says here, but I'll just summarize, is like it tells OpenGL how the bytes are ordered within our buffer. I guess you could sort of think of this as like how we had to do in our vertex array. We have this whole system for like describing our vertex buffer. This layout is very similar to that, except we just sort of choose from a number of predefined options. But you don't have to. They don't have to be predefined. You can see there are 4 memory layout qualified: shared, packed, standard 140, which is the one we're using, and then standard 430, which is the one you'd use with SSBOs. So let's look at shared and packed first. So packed, it says the implementation determines everything about how the fields are laid out in the block. The API must be used to query the layout for the members of a particular block. So this is just a lot of overhead. Like, we don't need to do this. I suppose you could, if you were very concerned with memory for some reason, you would need to do this so that you don't waste any memory, and you let OpenGL like optimize everything for you. But that's not what we're like. We have no reason to do that at all. Then the next one is shared, which says that it works like packed, but a little bit different. So it guarantees that all the variables defined in the block are considered active, which means that nothing is optimized out. So this isn't relevant here, but it is kind of cool and not something I've really talked about. If I have some, other uniform, I don't know, whatever it is, but I don't use it in my shader, or it is contained in like a path of execution within the shader that will never happen. So like if I have like if 0 I plus equal 1 or something like that, that would probably also be optimized out. But basically any variables that are taken into a shader that are not used in any way to affect the final output of that shader are optimized out. So that's what that means, is that if you use a shared layout, no matter whether or not the data in your block is actually used, it won't be optimized out. And I'm not sure why that's useful. Maybe for some debugging stuff, I'm not sure. But it has this other thing. The members of the block will have the same layout as the block definition in another program. So that's what this shared means. And I'm not sure if by another program it actually, I'm assuming it actually means like another sort of shader pipeline, like a set of at least vertex and fragment shaders. So I'm not sure why you would need that. I guess if you have like different shaders that perform, well, maybe perform different things, but take in the same inputs, like the same sort of data type, like your own custom defined blocks as input, it would be useful to only have to make sure that the memory layouts between those are the same, just so you don't get any errors uploading stuff. But obviously, we're not interested in that. So the one we're using is standard 140. And the reason for this, the big reason, it alleviates the need to query the offsets for definitions. So what that means, this is just talking about what pact set up here, which you can read on your own, how you need to use the API to query the layout. But standard 140 figures all that out for you, so we don't have to set any stuff in particular. But it is quite weird. The layout explicitly state the arrangement, an interface block, blah, 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 blah. Interface block can be shared across programs, much like shared, so we do actually get that same functionality. The only downside to this layout type is the rules for packing elements into arrays and structs. Alarm bells should be going off. We have both struct and an array of structs here. Can introduce a lot of unnecessary padding. So these are like well defined. They're not like, well, they are weird, and it's sort of just stuff that you have to learn through experience. But like, it's not random behavior. There is actually a specification for this. This is 4.5. We're using 3.3, so I'm not sure if it's changed. Maybe. But among the most important is the fact that arrays of types are not necessarily tightly packed. An array of floats in such a block will not be the equivalent to an array in C or C++. So that's what's going wrong here. It says the array stride, the bytes between array elements, is always rounded up to a vec4, 16 bytes. The bytes between array elements. That's our issue here. We're storing vec3s, but these are being rounded up to vec4s. And so what that means is that our position and color vectors are sort of getting mangled a bit, because what GLSL will read this as is like a vec4 of pos and then a vec2 of color, essentially. So like the first component of color here will bleed into the position, which isn't going to be used because we're doing nothing with the W component of position. But what this does mean is that, and I might draw something out for this. I think I'll go ahead and draw something. Just delete all this. So let's say we just have two lights. So each of them has a position, which is 3 components, and a color, which is also 3 components. But the way this is turned into bytes, the way GLSL receives this data, because it is rounded up to a vec4 instead of vec3s, which is what we're using, this stuff gets weird. So like the first 4 bytes will be, I'll call these pos1 and pos2 so that it's extra clear. So the first 4 bytes will be pos1 dot xyz, that's 3, and then color1 dot x, so that's 4. And then we have another 4 after that, which will be color1 dot yz, because that's all we have left. We've already read x, we just have yz, and now we need 2 more. So that's going to be pos2, the next element in memory, dot xy. And this is why we're getting yellow. Because we have sort of this bleeding over of position into color. So what we're expecting is to have a vec3 of pos and color. What we're getting is a vec4. What OpenGL is turning this into is a vec4 of pos and color. And what that means is that our position, as I said, the W component is unused. So in our case, the light we're defining, let's see, where was that? In our map, we have 100, 100, 10, and then 1, 1, 1. Okay, I'll just write that out. So we have pos equals 100, the X and the Y, and then 1 or 10 in the Z, and color, which is 1, 1, 1, which should be white. But the way this is getting read, or sort of chunked up, is 100, 100, 10, 1. So that's our pos. And then our color is 1, 1, and then we haven't set anything else, so it's just 0, 0. And wouldn't you know, this is red. Can't click. This is green, and this is blue. What do you get when you have just red and green and no blue? You get yellow. So that's why our light is yellow, because our color is being read as part of the position. And if you had more lights, the effects would just get even weirder, because obviously this stuff is going to shift by sort of 2 elements, because we have 2 extra elements for each light. So I don't even know what that would look like, but it's weird enough with just 1. So that's what's going on here. And we can see, I believe there's even an additional warning. Yeah. Implementations sometimes get the standard 140 layout wrong for vec3. You're advised to manually pad your structures and avoid using vec3 at all. And that's what's going wrong here. Like, it is weird. It's stupid that this is like an issue, but at least it's documented. This is like a well-known thing. So we're just going to have to conform to that. So we can't use vec3. Don't use any vec3. So we're going to use vec4. Now this will create some slight problems in here, in that we're doing math on vector 3s, but we now have vector 4s. So we just want to ignore the W components of both of these, because our lights aren't going to have an opacity, the 4th component of color. That doesn't make any sense. And position, obviously we just need X, Y, and Z, so we're not going to use W either. And the cleanest way to do this in GLSL is a cool thing called swizzling, where you can use this like dot syntax as if you're accessing a member, but then you can specify multiple members. So we just want X, Y, and Z, and it'll turn that into a vector of the appropriate length. So if we just did X, Y, it would give us a vec2, and I believe you can do this in any order you want. So this would give you like another vec4, but just reordered. But all we want is X, Y, Z for both position and light there. Okay, so now let's run and see what we get. Still yellow. So even though we've fixed our shader, what we haven't fixed is the data we're giving to our shader, because this is now vec4s. And the data we're giving, if you remember how I said this was suspicious, we're giving it as a float pointer to lights. So it's just going to take this float pointer and read, each light is 6 floats, it's going to read those 6 floats as a single thing, which was kind of fine before. Like, that part was working, it was just OpenGL weirdness, but now we have the opposite issue, where we fixed the OpenGL weirdness that we need to conform to this standard 140 layout by making these vec4s. But now we sort of have the same issue, just in a different place, where we're uploading 6 floats worth into a block of memory that expects 8 floats, 2 vec4s. So we are going to have to add some padding, and that's sort of what that documentation was saying, is that it's annoying because it incurs unnecessary padding. So I'm just going to separate these out to make it a bit clear. So we have our vec4 position here, and then we have our vec4 color. So we, as I've been saying, we want X, Y, and Z. Those are the components we're actually still using, but we don't care about W, which is the last element. So I'll just create 2 padding variables here, called padding1 and padding2. and just set them to 0. It doesn't matter at all what you set them because we're not using them. But as long as you have this layout in your light struct, it'll line up with GLSL, because now we have 4 floats, 2 for our Vec2 here, 1 for intensity, and 1 padding that we're not using, but at least it's there. And then same for Vec4. We have 3 floats in an array for RGB, and then padding, which we're not using, but it needs to be there. So now this sort of strategy of uploading everything just using a float pointer should work just fine, and we shouldn't have to transform our data at all, and it should remain very clean, just as we have it now. So the result we're expecting here is white light, and perfect. That's what we get. And we can even, take this a step further, prove that it actually works. Let's say now we really want yellow light. We can take that 1 away. There we go. And if we want green light, red away, and it works just as you'd expect. So this is actually it. This is all we have for lighting. I think I'll talk a little bit more about why the system is bad just before we go. Now that we've sort of written all of it and you've gotten to see it. So the reason this is bad is the way we've written our shader, essentially. Because our shader, it takes in an array of lights, and for each pixel, it has to calculate the effect of all lights on that pixel. Now this is the effect of all lights on each pixel, each frame. So for a standard 1080p HD monitor, like this one, the one I'm using, if you make this full screen, that's 2 million something pixels. That's a lot, assuming this whole thing was textured. We only have these, so it's not quite as bad. But if this whole thing was taken up by textures, this would be slow. And it is slow, especially if you have a lot of lights. Now, what you would actually do in a game engine is you do need some level of this. Like this sort of dynamic per frame light calculation is necessary if you have lights that are moving around. Which I think we'll do. I'm not sure. I might leave that up to you guys because it won't be like that difficult to implement. But either way, if you have lights that are actually moving around the screen, then you need to update those every frame, like send them a new position and all of that, and then calculate those dynamically, on the fly as stuff moves around. But for static stuff, static lighting built into your map, which is what this is. This light, we set it once here, we're never going to change it. Like we can't. We don't have a way to change this. That's not part of our map pipeline. All of this stuff is static. All the geometry created here and all of the lights created here are static. So the way you would actually do this is you would go through all the lights you have, like in your chunk constructor that you take in here, and you would create a texture for them. You would sort of do whatever algorithm you have here to calculate the effect of light at any given pixel. You would have the same sort of loop, but bake it into a texture. So you just have an array that is, big enough to cover your entire chunk, which is another reason we're not doing this. I'll talk about that a bit more. But you would take an array like uchar light data and make sure that's big enough for, we don't have this yet, but you would do like, width times height or whatever. That being the number of total pixels covered by all elements in the chunk, because you want everything in the chunk to be affected by lighting. So you would have to calculate that and then create a light array for that. And then you would do like for light and light in constructor.lights. And then you would do some simple transformation math here to take the coordinates of this and map them onto this sort of local coordinate system, the chunk local coordinate system. I think all you'd have to do actually is just subtract the chunk's position, this. But you'd basically figure out where this light is relative to this texture, and then do all of this same processing, but bake it into the texture. And then in your shader here, you would have like a uniform sampler 2D of U like light map or something. And this assumes that you're only doing like at most one chunk per draw call, which we definitely are only doing that. So this is fine. We only need to reserve one texture for the light map. But that's just a texture, right? And then all you'd have to do, you would still have to do this, as I said, for your dynamic stuff, but that will generally be a lot fewer lights than you'll have statically. So you can essentially like ignore that, and there's no way to fix it anyways. And you would just have another like texture call to U light map at the given texture chord. Well, no, not at the given texture chord. You'd have to do some custom math to like map this position into the current chunk, which would be simple. You just have to upload like the position vector of the chunk. But basically, my point is that it's just another texture multiplication. You take the color of all your dynamic lights, the additive result of all of those on the current pixel, the actual color of the pixel in the current texture that you're drawing, for the current triangle, multiply those two to get what we have now, but then further multiply it by the value in the texture in the light map texture, which is just going to be it could be colored, I guess, or you could do all white if you want to save on data. But that's just going to be another multiple between 0 and 1. And that's sort of like the fundamentals of this, I guess, is that that's all lighting is it's multiplication by some existing color between 0 and 1. 1 giving you full intensity, like that, full brightness color, 0 giving you black, and then everything in between will be some shade. That's all lighting is. And so that's how you would actually do it for this static stuff at least. But again, because of the way that I've had to do like this super sort of hacky, like very loose and general map format, there's actually no way to guarantee that stuff contained within your chunk is within a small enough area to be mapped to by a single texture, because there is a hardware limit on the size of textures. I think it's 4K, 4096 by 4096. There might be more these days, I don't know, but I think my graphics card is 4096. Unless you impose some like either artificial restrictions on the size of a chunk, which I didn't want to do because that's a lot of work, or you have potentially multiple light maps per chunk, which I didn't want to do because that's a lot of work. So yeah, that's the reason we didn't do this, other than according to the survey, like people just weren't that interested in it. And I can see why, because this, like, doing that would be very boring work. Like this stuff that we've done here, this is the interesting part. It's like actually some neat math, and it gives you some neat effects, and we don't have to worry about it being super efficient. And really, what I just explained to you, I probably did a poor job, and I talk fast, so I'm sure you didn't get all of it, but you could sort of take that information and what you already know about textures, basically, and just do it yourself. Like it would not be that difficult. So that's why I sort of left it out. So let's just run one last time here to see what we've got, and then I'll give you guys a couple cool sort of custom fake lighting equations that I came up with that I think look really nice. Because this one is sort of just smooth lighting, which is fine. It's not bad, definitely. It's serviceable. But I have some that I've written that I think are potentially cooler, and that you might want to use in your game. So I'll just go ahead and comment all this stuff out. Don't want to delete it. So this first one will be sort of concentric rings of light. And this will have some other uniforms that we need. But I'll just write it and sort of leave it up to you guys more or less to decipher it if you want. So we get the actual distance between our light vector and the pixel position. Yeah, that's right. And then we'll take in another uniform, which is the pixel size, or sort of the the size variable we've set here in our map, and round to the, just sort of truncate to the nearest multiple of that. And we'll have our fake lighting curve. Float intensity, max of 0, because we don't want any weird negative stuff. Okay, and then we'll have this other like hard-coded value up here. Hashtag define light distance. I'll set it to 255. It's a nice value. And then of course we need to take in our this U pixel size here, which will just be a float, I think. That should cover it. Okay, and then I guess I didn't need to comment that out. We can just use this same additive operation here, taking this sort of intensity calculated from the fake lighting curve and multiply it by the same color. Okay, so now we actually have to set this in our, we should be setting this in our renderer. Where is that? I don't think I have it pulled up. In render.cpp, we'll go ahead and do it whenever we clear. Set uniform 1f is called U pixel size, and this will be mengine.gl.psize. Okay. And now, because this light distance is now out of 255, I sort of have to change the scale of this. Set that to 100, because 10 would be very dark. And you can see here we have these, I should set it a bit darker, I guess. These are like concentric rings of our light. And it would probably be better if I make this a much bigger grid, just so we can see the whole thing. There you can see the concentric rings. They do die off rather quickly, which I don't like. I spent a lot of time messing around with these lighting curves to try and get them better. But at a certain point, there is like, it is a hardware issue. Like there are only so many shades that your monitor can display, or that your frame buffer can hold. And so you might need to use some other things, like you can use floating point frame buffers, which might help, and just sort of getting these values near black, getting more values near black, essentially. And in this case, like this method, this is artificially made worse. There are fewer shades between this and black because, you know, we're sort of just like doing it in steps of shades, according to our pixel size. So that's a nice concentric rings thing. You can change the size of the rings if you want. I've just used pixel size, but you could do some arbitrary thing if you want, just like 10. And that would make them thicker. That. But yeah, so that's concentric rings. And then one last one, which is my personal favorite and the one I actually use. Is sort of similar, except so I guess I should explain what we're doing here is like intentionally losing accuracy, I guess, where we are getting the length, the distance between our light and our pixel, and turning that into an int. We're like rounding that down to the nearest multiple of some arbitrary thing, which, as I just showed, turns out to be the sort of width of each band of light. So we're losing accuracy there by sort of artificially truncating this length from what would be a smooth sort of floating point number into just an integer or a multiple of something. So that's what we're doing here. And the area we're losing accuracy is in the distance between the light and the pixel. But in this next one, we're actually going to lose accuracy in a slightly different place right here. We'll have float z light at I.pos.z times light distance, which I will just leave the same as 255. And then our intensity will be quite a complex equation here. Hopefully I wrote that right. Let's just run and see what we get. Oh, I seem to have messed something up. This is why I love the like having the shader thing yell at you every time you try to set a uniform, because it makes it very obvious what's going wrong. In this case, though, that's not actually an error. That is just because we're not using pixel size. And I guess this is an example of like this being optimized out. As you can see here, we are still taking in a uniform, and we're setting that uniform every frame, but we're not actually using it in any of our active code. So it'll yell at us because we don't need to set this anymore. So I'll just comment that out. But what actually went wrong here, I'm not too sure. I probably just typed something wrong. It might also be that. Let's just try that. There you go. Now, if you look at this closely, and again, I'm not sure how well this will do with all the compression on YouTube, but what this does is it gives a unique, well, not unique, but it calculates lighting intensity per simulated pixel. So it's not just based on linear distance, as the concentric rings one was, but it is based on sort of truncated distance between like localized to the current pixel. And I think this is an excellent effect. I think this looks really good. Again, you can sort of see at the fringes here, it's not great. Like the color gradient there is not very smooth. It doesn't look great. It's sort of like pretty good here, then it sort of turns yellow and then bluish and then yellow again. I'm not sure. I don't think that's an error in my code. I think that's just a result of the fact that we're using like the default frame buffer instead of like a floating point one, which has greater color accuracy. Or it could be my monitor, I'm not sure. But I think this is an excellent effect for like 2D, sort of fake pixelated games. And this is actually the one that I have implemented in my personal game engine I work on. I think it looks really, really cool. Now, some stuff about this one, I guess. This, I guess I'll explain the difference between this and the previous one. So the concentric rings, we take the linear distance, like the actual linear distance between the light position and the pixel position. And then, once we have that linear distance, that completely accurate linear distance, then we round to a multiple of something. And what that results in is smooth, like circular shapes, as you saw. But what happens when we sort of move that accuracy loss inside of the length calculation is what you see here. We take the floor of this V position. Now, if you remember, V position is smoothly interpolated across by OpenGL for us, but ultimately the units that it's in is world coordinates, world space, because we just take in this from here, which is from our vertex buffer, and all of that data is in world space. You can see here our x and y coordinates are pos.x, which are set in our map data, which are world space coordinates, and we add these like width and height. World space in our case meaning like 1, like the value of 1 means a simulated pixel, the size of a simulated pixel. And that's why this works, is that we round down to the nearest multiple. We take floor of that. So essentially, if we have like 1.753, that'll turn into 1. So it rounds it down to a multiple of pixel size right there, just sort of inherent in the way that our data is passed in. and then multiplies by 2. This is just an arbitrary value here, just because I think it looks a bit nicer. Then we take our light position. We have to multiply by light distance here because we end up dividing. And then this is a bit weird. You probably recognize this. This is like subtraction here on square root of all this, and this is just circular. So z being like the intensity of our thing, and then x being I don't actually remember what I did. Like I graphed all this out in Desmos and stuff. But the reason, and I guess I can just show you, the reason that I have this sort of weird like ternary conditional here is that if x is greater than z, so if the length between the light and my position is greater than the intensity of that light, I return 0. Otherwise, I return the actual computed value, also just clamped between 0 and 1 just in case. But the reason for this is if I do square root of, I don't know, 5 times 5 minus 3 times 3, or I should do 25 minus x squared, you get a semicircle. And this is actually negated somewhat. It's like flipped upside down for our lighting curve. But my point is that you get this sort of rebound effect once you pass this threshold value. And so if I go in here, and I just take out this conditional altogether, you'll see something pretty interesting. So this all looks good, but then once it gets down into 0 here, it's sort of like rebounds back up to 1, and then eventually gets greater than 1, and OpenGL doesn't know what to do with that, so it just turns black. So again, this is like a completely, totally fake lighting curve, but I just think it looks really cool. And to do that, you sort of have to fudge the numbers just a little bit. But yeah, this may have been longer than an hour and a half, but hopefully this sort of last 20 or whatever minutes of playing around with lighting stuff was fun. I just thought I'd give you a couple options that I discovered for you to use in your own games if you want, because I think they're pretty cool. But other than that, yeah, we are done with lighting. Just keep in mind, again, that this is like inefficient, and for static stuff, you should be doing light map baking and all of that I described earlier. But for us, this is fine. I'm just going to sort of wave my hand and say, yeah, whatever. You can worry about that if it becomes a problem for you. not my problem. So yeah, we're done with lighting. Next time, we will start work on dynamics. So just stuff actually moving around the screen. And this I would expect to take at least 2 sort of lectures. There's a lot going on, and there's sort of 2 big components to it. And we will have to do a somewhat significant amount of refactoring to our graphics library, just to add like support for everything we need. But yeah, hopefully you are looking forward to that, and we can see all of our dynamics moving around in the world and being affected by all of our lighting in real time. It'll be really cool. So yeah, I'll have a new video out for you at least by Wednesday, but probably before then, probably Monday or Tuesday. And we will start on it on dynamics. So I'll see you then.